Okay. So, uh, for differential equations, the class, we have to come up with a final project, and our group is doing golf modeling. Okay. Now, what I want to do, you know me, I want to go crazy on it. I want to use OpenSim and OpenCap, and I want to like really make a true biomechanics model. But we're probably not gonna do that. We're probably just going to do like a really basic model. The professor's like, stick to linear models, and he's a really particular guy, so we'll see. But in any case, we are gonna read through this book that we found. Well, I'm gonna read through this book that we found on golf biomechanics, and it's like a whole thing. I think there's a bunch of. I mean, this is a long ass book. Actually, I should read through this. Okay, so this will be pretty simple. This will probably be a good idea to review. And I think he actually has some citations too. Um, torques. I mean, all of this is basically just physics. The torque is the. I think this is the moment of inertia times the angular momentum, or the. I don't know. I need to. We'll definitely need to go over that. Energy and momentum. I mean, all of this is just, you know, basic physics. Oh, yeah. See, I mean, this book is long, bro, but we definitely want to get into that too. I mean, he gets real detail into it. Muscle tissue, joints. Yeah, I mean, I think honestly, if we read this book, we get pretty far. Okay, now here we go. Um, this starts to get to the actual. All right, so let's just get back to basics though. Remember, okay, so what I read a little bit of this beforehand. Okay, units of measurement. Okay, vectors. You know, it's funny because like learning about vector spaces, but then you think about like a vector space that has units attached to it, and then suddenly you're like, oh shit, what is all this about? Okay, but I mean the general idea is the same. I mean, if you know what a vector space is, then you're probably pretty good. All right. Resolving vectors. A vector's resolved. This is probably a basis thing, isn't it? On each axis, we. In the diagram, we have an XY two-dimensional axis system. Resolving the dark blue vector means finding the x and y component vector such that they add up to the, okay, so the two light blue vectors are the components we seek. We know they add up to the original vector because they, yeah, tip to tail, they, whatever. Right, okay, so this is what he's trying to get at. Yeah, because that's the thing about physics, is that it always gets complicated by the fact that you actually have to put it in the real world and that you have to choose your stuff relative to something. So it's like, are you choosing it relative to the ground, which is presumed to be a plane, or are you choosing the plane of the actual golf club? Okay, so similarly, we can resolve a vector in 3 dimensions. Okay, so I get what he's saying here. We don't need to keep going. Wow, he modified this just last year. That's pretty sweet. All right, physical principles for the golf swing forces. Okay. Let's start with what a force is. It's a simple push or pull. What it ultimately does, and why we're interested, is it causes the object to change its motion. In order to sharpen the idea of what a force is, let's say what it's not. That's the thing about physics, man. I really like physics, honestly. A pair of forces, torque, the hands, yeah. We have to be careful when we itemize the forces involved in any analysis, making sure that all forces are individually accounted for. We shall see later that they can be combined for the analysis, but they first must be quantified individually. A force is not a mass. Yeah, I always confuse this too. The diagram shows a pair of 1 kilogram masses. The one in space with no gravity exerts no force. The one in a gravity field, say on Earth, does have a force exerted on it. We call that force the weight of the object. Weight is a force and is not the same as mass. On the other hand, force and mass have an intimate relationship, which is completely described by Newton's second law. There is a gravitational force on mass. There is? Relative to what? I don't know that. All right. A force is a vector. It has a magnitude and a direction. Since force is a vector, We can add forces together, but we have to add them as vectors, and we can resolve them into components. Right. Both will happen a lot as we examine how a golf swing works. Isaac Newton's greatest is the 3 laws about forces on objects. First, we will look at the kinetic implications of these 3 laws, and that is how forces between objects interact. All right, later we'll look at the kinematics, just the motions themselves. We do that because it is one of the biggest problems I see when golfers or golf instructors or TV commentators discuss. Here, I'm going to zoom in a little bit more. Discuss motion. Their confusion of acceleration, velocity, and position is serious. Yeah. If you want to understand what is going on, you need a more proper understanding, which brings us to Isaac Newton's greatest contributions to mathematics. Once Newton realized that his laws demanded a rigorous treatment on position, velocity, and acceleration, he invented a new kind of mathematics to deal with it: calculus. We will not be learning calculus here, but we will go through a bunch of examples of motion and you'll see some patterns. If you can retain some of these notions, you will at least partially immunized from silliness. Okay. All right. Newton's laws. The first law. This is fun, dude. I haven't gone through mechanics in so long. All right. Newton's first law. A body in motion stays in motion at the same speed and direction, same velocity, unless acted upon by some force outside of the object itself. Okay. If a body is sitting there, not moving, it will continue to sit there and not move. If a body is moving with some velocity v, both speed and direction, then it will continue to move with that velocity unless a force is applied to the body. What? You mean it won't slow down over time? That's exactly what it means. But remember, that's because of a force it stopped, a friction force. In space where there's almost no friction, things will go on moving for millions and billions of years. Okay, great. Stimp. What is this? I'm down to just kind of like goof off.
So today we're going to talk about the stimp meter and how we do that. So I'll kind of show you what we do. It's not very scientific, but so you put a ball in this notch here. This is a stimp meter, and basically just lift it up until it rolls off. Just kind of lift it up slow. And there it just rolled off. We do several balls. Then we measure that distance from the end of the stimp meter here. And then we'll do the same thing on going the other way, just in case we're going uphill or downhill or whatever. So right there.
Right, because I mean, this is more for a putt, but
we're at about 9 feet. We'll go the other way and see what we got, and then take the average. So now we're going to go the other way and take that measurement. And you can tell now we're probably going downhill. And previously we were going up. Oop. Didn't get that quite exact, but so that there, it's probably like 10.5. So today they're running probably a little bit slower, but they're right around 9.5, maybe close to 10.
All right. That's enough of that. Come on. All right. Oh, so you can use it to estimate how frictionless the ball and the surface really are. In the diagram, we show the conditions. Okay. Shaggy green 5. Fast green. This plane can't be done on dirt. It has to be smooth, hard surface. Concrete or blacktop might conceivably work. I've never heard of this. That's so interesting. Okay, so at some point you got to start moving the dimples and all that stuff. Okay, cool. Before we go any further, Newton's laws refer to a body or an object. It is a real physical thing with a mass, a size, a shape, everything that we think of a real world object of having. In real physics, it may be as small as an atom or as large as a planet, but in golf, we are not going to encounter objects much smaller than a golf club or a human body part, or larger than a person. Golf only deals with Newtonian physics. All right, yeah, I love that this guy is so funny. I love that he includes that. All right, we're not doing that. We're not doing quantum physics, and we're not doing relativity when we're talking golf. But I love to think about a guy who's like, hold on. What is the Hamiltonian of this system? You know, and someone's about to make a putt, and we're like, hold on. Yeah, it's sick that he included this 10 zeros thing. Okay. Okay. Second law of motion: if a force is applied to a body, the body accelerates according to the relationship F equals ma. The first law said that things don't change their motion without a force being applied. The second law says exactly how the motion changes for a given force. For purposes of discussion, we apply basic algebra and the acceleration becomes a force divided by the mass. This way we see what happens to acceleration as we change force and mass. Acceleration is defined as the rate of change of velocity. It isn't how fast something is moving. It's how fast we are changing how fast we are moving. Acceleration is a vector. It has a magnitude and a direction. The direction is the same as the direction of the force vector. Acceleration's magnitude is proportional to the force. We know from A equals force over mass. Increase the force and you increase the acceleration by the same percentage as you increase the force. Double the force, double the acceleration. Acceleration's magnitude is inversely proportional to mass. Increase the mass and you decrease the acceleration by the same percentage as you increase the mass. Double the mass, half the acceleration. Yeah. Oh, wow. Look at this picture. Is that for real? Look at how squished it gets. That's actually crazy, man. I didn't realize that a golf ball gets squished that much. That's pretty crazy. All right. For our example of Newton's second law, we'll do something that involves numbers. Only fair since the law itself is a formula. Let's figure out what the magnitude of the force of the driver face applies to the ball during impact. Let's assume that the impact produces a ball speed of 150 miles an hour and that the force is constant during the impact. The latter is a false assumption, but we'll make it to keep the calculations simple. At the end of the chapter, we'll revisit the assumption and see how we can do it more realistically. Okay. I mean, the thing is, golf physics are actually pretty... Yeah. So here's a diagram of what we need to know in order to solve the problem. The photos of the ball... Dude, I love these links, bro. I love just getting into something like this. Like, I don't give a shit. I don't fucking care. But, you know, people care about this stuff, and it's, like, cool.
My name is...
Whoa, they actually... Oh, dude. No way. They got a testing setup, bro. That's crazy, bro. That is so sick. Look at that robot.
And I'm the head of test methods development at Titleist. test
That's
methods development,
fucking awesome,
builds
man.
and maintains the test equipment that R&D uses to test our current products and all of our candidate products.
See, that's the thing is though, like golf is one of these kind of high-end sports, so like they got the money.
That are in development. Today, we've got a high-speed camera, and we're looking at driver impacts on a variety of balls and a variety of ball speeds. And we're doing that as a teaching point for videos to show people that even if you've got a lower driver speed, that you still compress the ball sufficiently. I gather there's talk out in the world that I don't swing hard enough to play the Pro V, or I don't swing hard enough to play the Pro V1X. Well, honestly, if you compare the 120 mile an hour driver speed to the 175 mile an hour driver speed, and you'll see
That's actually nuts that the club is moving 175 miles an hour. Is that real, dude? That's pretty crazy.
that the compression on the ball is really quite similar. Today we're shooting 22,000 frames a second. That gives us about 10 or 12 individual frames of the ball on the club face. We've got an exposure time of 15 microseconds, which is a little bit long, but I wanted the images to be nice and bright. We can take measurements of the ball, and we know precisely what the time is from one frame to another. So we look at it as a series of still pictures, and we can look at the mechanics of how the
that's
ball
so cool, man.
impacts the club and how that translates into spin and speed and launch angle. The first time we did this, there were a bunch of things that the ball does that I really didn't expect. We did expect that the compressions would be similar. That was part of the point of going through this exercise, so that wasn't a real surprise. But when the club comes into the ball, ball's round, as best that I can do round with my fingers, the club comes into it, and this side of the ball goes flat. And there are 3 or 4 frames where the ball looks like a D, flat on this side and round here. And then...
Where's that picture? Right, yeah, because it's not like it... Yeah, it does look like a D. He's right.
Right before it's done, the backside of the ball pulls in like that and then goes out. When it comes off the club face, the ball is actually longer. It's not round anymore. So it does, spring right off the club face. And
well, that's interesting because this looks like a
It's one thing knowing that happens. It's a whole nother thing seeing it. It's really cool. It's a lot of fun. We have used this camera and this kind of setup to look at how the ball responds, contact time, how long the ball is on the club face.
Dude, look at that thing, man. I actually want to know about how they designed that thing. Do they have other videos? Dude, what a badass video, man.
Look at how the ball responds, contact time, how long the...
Because see, I think they have 2 motors. I think that
is on the club face on a wedge.
I can't tell. I honestly can't tell. We need to get like... Most of this is going to be just boring golf stuff. I want to see more about that test setup. Let's look at robot. Do they sell the robot?
You are here to learn all about the Titleist GT3 product.
Where's the fucking robot, dude? Are you kidding me? Dude, this is the thing that's so annoying. Is like, these guys don't care about the robot. I care about the robot. Where's the robot? That's what I want to know.
Cool material.
They have a poem here? Hilarious. Alright, whatever. This isn't an ad for Titleist. I do want to see the robot because I want to know if because the thing is the robot is sick because you get ground truth with way less variability than you're gonna get with a human. I expect. I mean, that's why you build a robot. All right, let's just look at this video then.
Paul Furs, and my name is Paul Furs.
It's too hard to tell.
I'm the head of test methods development at Titleist. Test methods development builds and maintains the test equipment that
Anyways,
R&D
all right.
uses to...
I would like to know, but I can't. Maybe that image will show you. Oh yeah, it definitely does. Yeah, so it is a double pendulum. It definitely swings. There's an actuator at the end of that thing. So they have a shoulder wrist model. All right. This video is sick. I love that video. All right. Okay, so let's do some math. We know the force is 0 everywhere except during the 0.4 seconds or whatever. What is this? This is going to be like a tenth of a second. This is a millisecond. This is like really small. What is that? 400 microseconds? Why is it so slow? Yeah, 400 microseconds. We know that the acceleration is proportional to the force. So the acceleration curve is the same shape as the force curve. I mean, okay. But the force applied is clearly not a step like that. But that's an assumption, and I'm down for that. We're given the ball's velocity is 0 before impact and 150 miles an hour after separation. Why do we know that? Because of the club speed? I don't know. Okay. All right. Wait. We will use the. Oh, okay. They convert to 67. Okay. No way, dude. I love that he links to the specification. That rules. That rules. I love that. Oh, I love the rules, bro. That's so fun. Where's the weight of the ball? What? Wait, is it USGA? Wow, they go to a 10,000? There has to be a tolerance on that, but that's so cool. What the hell does this mean? I've literally never heard of that. Avoir du poids? I've literally never heard that. All right, anyways, we do not need to go down this rabbit hole. Okay. So let's get started. The constant force requires a constant acceleration because the mass doesn't change and F equals ma. Now remember, the definition of acceleration. Since the acceleration is constant, the velocity changes the same rate. Right. So for each, yeah. Okay. If we can find the acceleration during impact, then we can find, if we can find that, then we can apply F equals ma to the force. There, the impact lasts that. Right, because we know that it changed 67 meters per second in 0.0004 seconds. Dude, this guy rules, man. All right, cool. Forces 1, covered. We already have F equals ma. What more do we need to understand how force produces motion? Okay. People ask. Because of F equals ma, we can correctly equate force with acceleration. The force graph over time is the same shape as the acceleration graph over time. The mass is just a scaling factor. It tells us how tall that shape is, but it's still the same shape. You know what? Deceleration always confuses me. It's like, anyways.
Y'all ready to see something different? Hey. All right, people. So that was the hip form cardio of car pushing. Got to catch the car right now. It's rolling back right now, but give me about another month. I'll push a Hummer. Thanks for tuning in.
Nice. Since force is the same shape as acceleration. In most golf physics, the velocity does vary. Okay, this thing about an integral. Okay. Okay. All right, curved motion. Remember that force is a vector quantity. That means that it might not be pointed in the same direction as velocity, nor directly opposed. For example, this picture shows a force at right angle. There's no component of the force that is wait, whoa. Remember, velocity is the accumulation of acceleration over time. If there's no force, then the path would continue horizontally. Gravity, yeah. Now let's look at more interesting complexes. Suppose the force changes as the velocity changes, so that the force is always perpendicular to the path. But we let the that's actually wild. It's very weird. Okay. Okay. What are the units of torque? Let's remember that torque is a force times a length. So the units would be a unit of, so yeah, that's why it's like Newton meters and stuff like that. Oh yeah, there you go. Yeah, like when you buy a motor, the motor is rated for, like a stepper motor is rated in Newton meters. Levers. So far we've been using photos as the basis of our diagrams. Most textbooks use stylized drawings to depict torque. They consist of a rigid beam or lever sitting on a pivot point called a fulcrum. Okay, we get it, right? Okay. Let's look at two special kinds of torque that have significance in analyzing the Gulf swing: the couple and the moment of a force. A couple is a pair of forces on an object, those forces being equal in magnitude, opposite in direction, not operating in the same line. Parallel and at a distance from each other. We've already seen an example of a couple turning the stove knob. The torque of the couple is the magnitude of each force times the distance between them. Yeah. Okay. Here's an example of a couple in the context of a golf swing. It is the hand couple, a push by the right hand and an equal pull by the left. In the context of a golf swing, the moment of force is critically important. In particular, and we can put more precision on this later. You use it to tell which way a force's moment will turn. Yeah. Okay, so yeah. Right. Moment of inertia is the same as mass. Okay. Rotation is a change of angle over time. So we should expect rotational velocity and acceleration to use units be associated with angles. In revolutions and radians. Wait, really? Is that real? I had no idea. Is it really a milliradian? That's so wild. I never knew that. Okay. Okay, yeah. So that's just the angular. Right. Okay, we don't. That's pretty basic. Yeah, it's okay. Let's say that. Let's go through it. Okay. The moment of inertia functions in rotational kinetics exactly as mass does. If you choose a different axis, does that change the object's moment of inertia? You have to specify moment of inertia about which axis. The moment of inertia is calculated based on how far from the axis each particle of mass is located. Wait, how did they? Yeah, why r squared? Remember that moment of inertia is the measure of a body's resistance to turning when a torque is applied. It's analogous to mass, the resistance of a body to moving when a force is applied. The linear formulation is more fun. We're going to explore how angular motion is a combination of coordinated linear motion of a lot of chunks. We know that r squared means we multiply r twice. It turns out that each time is a different rationale. Okay, in the diagram, the gray rod is rotating through an angle A. I've marked two particles of mass, one blue and one red. The red one is twice as far away from the axis as the blue one. In order for the object, the gray rod, to rotate through angle A, the red particle has to go twice as far as the blue particle. In general, the distance is proportional to the radius. Let's see how each particle contributes to the total moment of inertia. We know that torque is equal to the angular velocity, right? Times the moment of inertia. So the moment of inertia is equal to torque over the angular velocity. We've just seen on the diagram that linear acceleration A is proportional to the radius. That linear acceleration oh no, yeah, that's not velocity, that's acceleration. Hold on. Bro, why is this so confusing? And I think work is joules, right? Kilogram one joule is 1 Newton meter. God, I haven't done this stuff in so long, dude. I should retake mechanics. Man, I haven't done mechanics in so long. Wait, is joules the measure of work? I thought it was time, though. God, this shit is so confusing. Alright, whatever. Let's just keep reading this. Yeah, I'm fine with that. Okay. Okay, so moment of inertia for a club is equal to the sum of I head I shaft and I grip. Okay, so you can compute all of those, and then you get this is the inertia of the club. So if I were to hold it at the butt of the club, that would be how hard it would be to rotate it about the butt. The interesting thing though is you hold it sort of towards the top of the grip, right? And then you also have this moment of inertia, presumably at the center of your chest or the center of your shoulders or something. So I don't really know about that. The shaft is only 80 grams. Is the club really that light? That seems kind of crazy. So the moment of inertia is going to be, so okay, we gotta just remember, so the torque is equal to the moment of inertia times the acceleration, the angular acceleration. So but what is the unit of measurement? Um, Huh. That's definitely not what that means. It's like a moment can be used in statistics, I guess. Um, Yeah, so it's like over here. It's like pretty close to the edge. Oh, there you go. There's the center mass. I think there's a Vsauce video on tour, right? I'm pretty sure he...
Hey, Vsauce! Michael here.
We'll watch that later. I don't like to watch full videos on stream. Really. Alright. It's clear that this is a really central concept, though. I need to understand moment of inertia. The mass times the square. Yeah, the perpendicular distance to the axis of rotation. That makes sense. The moment of inertia of a rigid composite system is the sum of moments of this component subsystem. Bro, this shit is crazy, dude. Why you get into this, man? I don't know. It's funny as hell. Mm-hmm. Mm-hmm. Sometimes you just gotta like bumble around like an idiot. But isn't there an SICM book? Don't they use Lisp? Let's see if we can find the book. Actually, would be good to go through this book. I want to see some lisp in here. I just want to see some lisp and then we can move on. Bro, what the fuck? There we go. There's some lisp. All right. Enough of that. All right. The smallest moment of inertia of the object is about an axis through the center of mass. Do I really need to know that? I feel like that's more detail than I really need. I mean, at some point, we actually have to do something real with this project. I mean, this is just crazy. But you know what? Let's like look up, or let's do golf club manufacturer provide center stuff. Like if we just went to title list, and we like went to a club, like let's look at their like most, I don't know. Okay. I mean $1,800. Like, come on. For $1,800. That's just for the bro, what? Dude, how is this thing $1,800? And then if you want the what is this? What are you even buying? This a custom shaft? I don't even know what the difference between that is. That's crazy. What do they machine this out of gold? It's ridiculous. Okay, but what I want to know is like data, schedule of fitting, specifications. Okay. Length lie. What is lie? I don't even know what that means. I am so surprised. I didn't realize that these golf clubs are fucking $1,800, dude. What the hell? Don't you need like 10 of these things? That's ridiculous. Ping? All right, whatever. I've heard. Okay, let's just try to go to one of the drivers. Let's see. Clubs, drivers. Let's see. What's their most expensive driver? Whoa, the drivers are cheaper than the irons? Is that real? Did you guys know that? I didn't know that. $200. Oh, you know what? It's $1,800 for a set, bro. You buy a set, I guess. Oh, you don't just buy one. Okay, you buy a set. But okay, so driver is more expensive. All right, let's see. Driver specs. Okay, let's I don't see any moment of inertia thing. I see a bunch of nonsense. Oh, here you go. But it's more of like a talking point. But you can change that. Oh, that's interesting. All right, I don't. Let's see. See, what's their newest club? Dude, stop. Dude, the optimization of this is hilarious. Okay, all right, let's suppose you have a rigid object. The hell? See, that's interesting. Yeah, it's like, what can you get away with? Usually we don't have a system as simple as a single torque and a single force through the center of mass. Yeah, because like I guess if I have this rod and I push it sort of off the center of axis. I don't know. That's an interesting quote. Okay. Collection of forces and torques into motion of body is easier than motion of body to forces. Oh, there's homework problems in the back of this thing, or is he just saying that? Is there actually exercises? Wait, which part are we on right now? I don't think so. What is it? Our job is to find a single force and a single couple that will produce the same dynamic effect as these forces and couples. So wait, first off, I don't even know what this means. What does that mean? By now, I shouldn't need to know, but I do need to know. When you describe the couple, I mean, I guess what I'm trying to understand is like, my understanding of a couple is that it's on the opposite sides, like it's like if the switch flipping. We're going to get the moments of all the forces about the center of mass. Get the total net force on the object. Right, it's like the perpendicular though. Oh, interesting. Okay, okay, okay. How did he get to this? It's just because the moment is equal to the force times the radius, right? So okay. The total moment is the sum of the moments. Now we can find the total net force on the object. We need to do vector addition for all of the forces. Since we have converted all the forces to x and y, we can do simple signed addition on the x forces separately from the y. So x is 15, y is 6. So we have a right triangle with sides 6 and 15. Here's our equivalent force couple system. The single force on the object acting at the center of mass is 16.2 pounds, acting to the left and downward at an angle of 21.8 degrees. The single couple, because we got 20 and 20, and they're both counterclockwise. We're going to start with a diagram that is very close to figure 1. Wait, what the hell is figure 1? Wait, is it this is the club head or is it? Okay, we have the weight of the club. We have the hand force. What is that force though? And the hand couple. Ugh, this is so annoying. Every now and then my mouse just stops working. Whatever. I don't care. The hand force and the hand couple vary during the downswing, which of course adds complication, but the weight vector is perfectly constant. All right, here's our club with the weight, hand force. Oh my god, my mouse is driving me fucking crazy. I don't know how this happens. Just like randomly does. Okay, so you're going like this. Maybe you're like this. And you've got a twist at that point. I don't really know what the normal force is. The tangential force. So let's say I'm just swinging my arms. We need to go back to that example of that guy like spinning that. This. chose to resolve the forces not to the x and y axes, but to an axis perpendicular and normal to the hand path. And another axis tangential to the arc of the hand path. Is the provider of hand speed. What is hand speed? That's just how fast the hands are moving, right? But the couple is what accelerates. Because what we care about is how fast the club is moving. It is true. It is only about 2/3 of the way through the motion of the club, but the club accelerates both linearly and angularly through the downswing. The first 2/3 of motion will occupy a much larger portion of the time. So the weight of the whole club is 410 grams. We found that the center of mass is to be 28 or 29 inches from the butt of the club, which is 25 from the mid hands point where the hand forces are applied. At this point, the hand couple is about 10 foot-pounds, and the hands need to exert a 20-pound normal force. Just to keep the club from flying off on a straight line. See, I don't get this normal force. The tangential force, which is creating hand speed, is actually a lot less than the normal force. So from the shoulders to, if I'm like this, but the club is horizontal. So I'm like that. So it's like this. The club is horizontal. And I guess the center point of my shoulders would be, since that's the center, that points to the center of the, what do they call it? The hand path. Because the hand path is centered about, okay. So then they set it into XY coordinates. The total X force where does the 7.9 comes from the 9, and the 9.4 comes from the 20, and then the total Y force is going to be, yeah, right, is going to be 17.7 minus 4.2 minus 1. Okay, so the whole club is moving like this, but then there's also a twist. The next step is the equivalent torque. We already have a hand couple of 10 foot-pounds counterclockwise. Of all the red vector forces on the diagram, only 2 of them contribute a moment. If I were to like push on it that way, right? Like that, I mean, this has to be exhibiting a torque on the club. These moving this to the shaft, did he specify that you're allowed to do that? Because that's not really. Anyway, so these things, since they're on the axis of the center of mass, if I were to pull on the club, since it's what I'm saying is, like, if you were to draw this as a vector and draw this as a vector, then this is not going to be a straight line. So these are the 2 torque arrows, is I guess what he's probably saying, right? Where does it say only 2 of them? Only 2 of them. All the rest pass through the center of mass, so the moment arm is 0, and they produce. The forces of interest are the 17.7 and the 4.2. So it's going to be 4.2 times 29. I don't understand this picture. Like, how is the club moving up? It's just moving like... But it's not moving up, right? The club is... The club is definitely moving down. Yeah, the moment of inertia is going to be way smaller when you don't actually. All right, we'll go through this. Let's just like skim a little bit more just to see where does the. Yeah, joules per second is power. Okay, that's kind of. I think that's what I was thinking of. Yeah. Yeah, a bunch of math, bunch of. Oh wow. Momentum mass times velocity? I mean, like, how is this the first thing? I'm using DuckDuckGo and I get just the most stupid stuff. Yeah, okay, momentum is mass times velocity. It's m1 v1 m1 times like the first the momentums before and after the have to be the same. Leave a divot? Does he mean like literally? Oh, that's a big ass B. You know, it's interesting. Look at how it starts to spin. See, it's definitely spinning. I feel like backwards. Okay, but where do we get to the biology? I feel like we should, yeah, here we go. Right, yeah, yeah. This is, yeah. Downswing is motivated by muscles contracting. LM. That's a good picture. But so what is, because typically, I guess you use your triceps, use your wrists. Because you go like this, right? So your arms are bent at the beginning of the downswing. Wait, I don't remember this. What? The classes of... Oh. Oh yeah, I've seen this. I've seen this before. This is crazy, actually. The fact that biology evolved this is like totally crazy. Oh my god, this gets really into it now. I didn't think about range of motion. Like if you're as like as fast as possible. But like, because it's not just constraints on the amount of force per, right? I guess if you treat that as constant, like the fastest that you could like contract your bicep completely, like, so there's a range of motion, and then there's, I guess, there's a maximum amount of force. And so what you want to find out is the maximum, because what you're trying to find out is the maximum velocity, right? At the end. I mean, it decelerates. So I guess, dude, the physics of a golf swing is actually really tough.
Hi everyone, Peter here from Flow High Performance, and in this video we'll be covering the meaning and implications of the force-velocity relationship. The force-velocity relationship has two parts, the concentric portion and the eccentric portion. While the relationship is essentially the same for both, it can be somewhat confusing to understand. Therefore, we will cover the concentric portion first, followed by the eccentric portion. The concentric portion of the force-velocity relationship is fairly intuitive. Concentric muscle actions are when the muscles shorten and produce force. This is the typical lifting portion of exercise. For example, when we stand up from a squat or lift the weight in a bench press. Essentially, for concentric muscle actions, force and velocity have an inverse relationship with regards to athletic exercises. This means that when force is high, velocity is low, and when force is low, velocity can be high. To demonstrate this point practically, let's take any fundamental barbell exercise, such as a squat or bench press. When the barbell is loaded with a relatively heavy weight, it will move slowly, even if the athlete tries to move it as fast as possible. However, the force produced will be very high since the weight is heavy. Now, if we load a relatively light weight for the same athlete and ask them to lift it as fast as possible, it can be moved much quicker because the load is lighter. If we reduce the weight even more, the athlete can move this weight even faster again. This relationship is easy to understand and makes intuitive sense. Now, moving on to the eccentric portion of the force-velocity relationship. An eccentric muscle action is when the muscle lengthens as it produces force. For example, this would occur when we lower the weight down in a squat or lower ourselves down from a pull-up. During this phase, force and velocity have the opposite relationship that concentric muscle actions have. This is because we can actually produce more force eccentrically than concentrically. For example, you can lower more weight than your 1 rep max down under control in a bench press, but you can't press it back up. And the more and more load that is lifted eccentrically, the harder and harder it is to control. Because of this, the weight can't be controlled as slowly eccentrically with very heavy loads.
Oh, interesting.
Therefore, the velocity increases. So as force increases, velocity of movement also increases. So what does all this mean for athletic training? Essentially,
That's interesting. I never
different athletic qualities exist on different parts of the force-velocity relationship. For example, exercises such as maximal speed running and plyometrics would have very high velocity muscle contractions and the lowest potential force production, while heavy weightlifting exercises would require much higher forces with very low contraction velocities. An exercise such as a power clean or a weighted jump may exist somewhere between these two extremes. So we can target different qualities based on how much we load an exercise and use velocity-specific exercises to transfer better to sport performance. For example, if we perform a squat jump for power development, we can load the exercise more or less to alter its force-velocity profile. Lighter weights will allow velocity to be faster and for the athlete to jump higher. Heavier loads will mean that more force will be produced, although velocity and jump height will be reduced. However, it is important to ensure that regardless of the load used, the intent should always be to move as fast as possible when training for athletic performance.
Dude, all this stuff is so confusing, man. It has center of mass too. Bro, this is gonna be way more work than I thought. All right, let's cut it off here. All right, I honestly don't even know if I got anything from the past 3 hours. It's clear that this is so much more complicated than I thought it was going to be. Wrist, shoulder. Okay, so it's actually this is going to take a long time. But that was biology 4. Oh, okay, so let's just look through this. All right, that's it. We got to cut it off at some point. All right.